Alright, so I think this will be our last video on convergence, though there's so much more to say. Really, we could probably do a whole course just on this and still maybe not finish it. But this is at least a pretty deep dive, and we can now talk about the spectral sequences that we've been looking at in this course and see how convergence works for them mostly. So where were we? Oh, I should say some good references here. I'm still following Boardman and McCleary, but I'm also going to mention the Bockstein spectral sequence. Remember, Palmieri had that nice note about the Bockstein spectral sequence, so that's a good place to look too. All right, so what was our setup? We had an exact couple, and that looked like maybe some bigraded groups, D, the map between them, or map back to itself, I, and we had E1 star star, and that was J, and that was K. And let's see, then we had DP star maps via I to DP minus 1 star, and so on. Okay, and so we had this tower, and then we defined D minus infinity, comma star. This was our colimit over that diagram. And we had the inverse limit, D infinity. And then, of course, the inverse limit is not exact, so we've got that right-derived term that looks like RD infinity, and that's just our lim 1. Okay, so what is sort of the main example that I've been trying to carry through this whole story? Well, that's where we have a filtered CW complex. So let's let X be a filtered CW complex, just with some nice cellular inclusions, but not necessarily the CW filtration. And the sort of easier spectral sequence is this E1 PQ homology spectral sequence. So that's the homology, the relative homology of XP comma XP minus 1. And notice in my other notation, I can make that E1 minus P minus Q. I think I mentioned this in the previous video, and so all of the things I've been saying for exact couples and convergence still hold for this homology sort of spectral sequence, but now I've kind of turned things upside down. Then what's my DPQ? Well, this should just be the homology of each of those filtered pieces, and that's going to end up giving me D upper minus P minus Q, okay? And so when I look at this diagram, of course, I've reversed my indexing, and so the colimit is going to be, well, okay, let me first say that X is, of course, the colimit of the filtered pieces, and so the homology, because colimit is exact, is the colimit of the homologies of the filtered pieces. Okay, so that works out nicely. And then this D infinity term, that's our inverse limit. Well, the inverse limit will eventually get back to the 0 space and then the minus 1 space, the empty set. And so that's just going to be 0. That is no homology. Okay, so the theorem is that, yes, this all works out as we've been saying all term long. So the homology spectral sequence with this whole setup that looks like E1 PQ is the homology of our filtration quotients or relative homology, and we write this arrow. But now we know really what that arrow means, so I'm going to say that this spectral sequence converges strongly. Okay, so originally, long ago, this arrow here meant that, okay, that we should end up with our E infinity term looking like an associated gradient of this thing, and that means we only need to solve the extension problems in order to cook back up the homology of X, and that's exactly what this means, converges strongly. So we just need to solve the extension problems. And why is this? Well, this is a half-plane spectral sequence. This is the kind where we have the good convergence, so where we have exiting differentials. And remember there, we saw that the half-plane spectral sequence would converge strongly to the colimit whenever that inverse limit was 0. So it's really just those two pieces put together. Okay, great. What about the cohomology version? Well, our cohomology spectral sequence looks very similar. We just take cohomology, relative cohomology, and then this is supposed to cook up for us the cohomology of our space X. And this is a little bit messier. So what we can say is that this converges conditionally. Okay, well, what's going on there? This time we have a half-plane spectral sequence with entering differentials, as we saw at the end of the last video. Okay, and those don't have as good convergence. So we have to be a little bit careful. This will converge strongly. Not always, of course. I'm about to give some hypothesis. So this will converge strongly if there's no inverse limit term. Sorry, the inverse limit is what it will converge strongly to if there's no lim 1, right? So if we have a lim 1, then of course we're never going to see that on the E infinity page. So of course this can't converge strongly. So in practice, in a particular situation, then really this does have fairly good convergence, especially if there's no lim 1 term. And often you can make some argument about why that would happen. But in any case, we're never going to get quite as good of a spectral sequence convergence for the cohomology case as we can with this nice homology case because the colimit is exact. Okay, maybe let me say also, these theorems that I've written down are actually better than this. So in both of these, more generally, you can use any cohomology theory. It doesn't have to be singular cohomology. So you take any spectrum and it represents a cohomology theory, and you could work with that. Maybe K theory, whatever it is you want to do. Okay, great. So that was one of our main examples. And remember that the Serre spectral sequence came out of a filtration of a space and playing a similar game, and it was just identifying the nice E2 page. So let me say that basically takes care of our Serre spectral sequence as well. We could write down the same things for the Serre spectral sequence. Homology is going to work out better, and cohomology, we're always not going to be able to see if there's a lim 1 term. So we'll have some conditional convergence. Okay, what other kinds of spectral sequences have we looked at? So another common one is to have a filtered chain complex or co-chain complex. that's really just, you know, which way do you index things. So let me be kind of agnostic. I'll probably pick co-chain complex just because I've been writing everything cohomologically lately. So let's say we have some filtered complex. Not necessarily a finite filtration. Of course, if we have a finite filtration, then everything's well and good. We get an exact couple, everything's bounded, it's all going to work out just fine. But if it's not necessarily finite, well, what do we have? So, well, the theorem is that if the filtration is good, then things are good. Huge surprise. Okay, so if the filtration of C is, what are all the things we want? The usual, so exhaustive, Hausdorff, and complete. Then, well, of course we have a spectral sequence. And we could write E1PQ. So I'm writing this cohomologically. Again, you could write the same thing homologically if it was a chain complex instead of a cochain complex. Apparently, talking about that made me want to switch mid-expression. Okay, so H upper P plus Q of the filtration quotients. Okay, and what does this converge to? Well, it converges to the cohomology of our cochain complex. And how does it converge? That's really what we're interested in now. So the claim is that this converges conditionally. And what does it converge conditionally to? Well, to the colimit. So as usual, that's my d minus infinity star. And we can identify that with the cohomology of our chain complex. And that's really just because colimit is exact. So, okay, so that's good. Why do we have this converges conditionally? Maybe that's kind of unsatisfying. Well, notice here that here we have no restrictions. I just said this is a filtered chain complex. I didn't say anything about the chain complex. So I'm saying this with no restrictions on the boundedness of the filtration. I guess it wasn't any filtration because it was exhaustive, Hausdorff, and complete. But, you know, in practice, often I want some kind of bounded filtration. Of course, if I have a totally bounded filtration, then I'm just going to end up with a strongly convergent spectral sequence. But if I don't have any of those kind of limitations, the best I could hope for is conditional convergence. Okay, let me just say of the filtration, since that's the key here. Okay, now I've been saying, you know, of course, if we have this nice thing on the chain complex, then we get the nice thing on the spectral sequence. Well, we actually have to be a little bit careful. So it's a little bit more subtle than all of that. And McCleary really goes through the details of the chain complex version, so you might want to look there. But just because, well, the first one's actually good. If you have an exhaustive filtration of your chain complex, then yeah, you're going to get, we're going to make the exact couple, and we'll filter the D infinity term and the D minus infinity term using image and kernel. I may have said those backwards. And then that gives us a filtration of the thing that we're trying to converge to. Here it's the colimit, so I guess we should just use that one in this particular case. But the point is that just because you have an exhaustive, sorry, in this case it's good, an exhaustive filtration of C will give you an exhaustive filtration in that sense. So all I was trying to say is it's complicated to get there to the filtration, but this will give us an exhaustive filtration of Hn. Okay, and actually, you know, the other thing I was saying is if everything's bounded, that's good. Bounded below will carry through. Bounded below implies bounded below for your filtration on homology. That's all well and good, but not everything goes through. In particular, Hausdorff does not imply that you get Hausdorff over here in homology. So this is not just a trivial statement. There's some work to be done here. There's some subtleties. In any case, we can say, well, all right, maybe let me say, of course, if things are bounded, then we do get strong convergence. If we want to relax these conditions a little bit, well, we really shouldn't relax exhaustive. Let's just filter the thing that we're after. But if we only had that, then of course we're not going to converge strongly. But what can we say? Well, we also have this theorem that if the filtration of C is exhaustive, so no assumption about Hausdorff or complete, then when we look at the spectral sequence, still not assuming any boundedness. Okay, so it starts with E1 page, the cohomology of the filtration quotients, and is supposed to cook up the cohomology of the chain complex. Well, if we don't start with something complete, then we're going to converge to the completion. And in fact, again, we kind of haven't dealt with any of the issues of limits and lim 1 and so on, so this will still converge conditionally. So this is the colimit. But now notice the colimit we would identify with the cohomology of the completion of the chain complex. Okay, and that's not so surprising, as we've seen that the spectral sequence can't tell the difference between completion and not. But again, this is something about the completion of the chain complex. And so there's some stuff to check here that, yeah, that's really giving you the right thing on homology. Okay, let's see. So our chain complexes are how we got our spectral sequence for a double complex, and that led us to the Grothendieck spectral sequence. So I think the last one that we need to come back and talk about, that we've seen so far at least, is the Bockstein spectral sequence. And that one looked a little bit different, though maybe not so different. I mean, we could think of it as just coming from a filtration, but let's investigate it a little bit deeper. So suppose that we're looking at the homology of some chain complex. Let's make it cohomology, I don't really care. And you look there and none of the elements, so I'll say nothing, is infinitely p divisible. P is some prime here. Well, what is that going to tell us? One thing that tells us is that we have no summands of anything like Q, right? That would have stuff that's infinitely p divisible. We also don't have any z mod, let's say z mod n, for n relatively prime to p, right? So that's already saying we're ruling out a lot of stuff. Well, then we could take our chain complex and we could filter it as we have before by the powers of p. And now I'm saying that nothing in homology is infinitely divisible, but I'm not saying that that's a finite filtration on C. It's definitely exhaustive the way I've set it up. So I just made C the 0th filtration, I suppose, or the first filtration, however we want to name it. Okay, the assumption on divisibility doesn't tell us that it's finite. but it does tell us, oops, keep accidentally switching between my pen and my eraser. Okay, so the assumption on divisibility will tell us that we get a Hausdorff filtration on cohomology. Okay, so that's kind of nice. And all right, so the claim is that our Bachstein spectral sequence I'm using S and T now because P is taken. Trying not to abuse that. Okay, well this is just coming from a filtered complex, so we've already seen that, and this converges conditionally. I guess this really converges conditionally to the completion. So let's do that. Okay, but this converges conditionally. Okay, well, in fact, we'll get a little bit better. We'll get that it converges strongly. There's a few different hypotheses you might need and would give you strong convergence. I'll just say one. So it does converge strongly if for each spot, we look at the PQ spot, there's some R, so that when we look at ERPQ, this is finite. Okay, so that's kind of a nice condition, and the reason is, well, our typical example where we use this is where C is actually singular cochains on X, and then the cohomology of this is just the cohomology of X. Well, I guess I can write that. But often this is finitely generated. So for example, if X is finite type, CW complex, then we'll get these groups to be finitely generated. Notice that all the groups in the chain complex, these are all free abelian. Okay, so we don't have to worry about that infinite divisibility kind of thing. Oh, sorry, no. We don't have to worry about the infinite divisibility because I want to assume these are finitely generated, right? And Q, for example, is not finitely generated Z module. So this is finitely generated abelian. We just have free summands and torsion summands. Okay, and so we're in this case where we have just got lost. Sorry. Yeah, we're in this case where we have this nice situation. Okay, what am I trying to say? We've got, remember, we have this short exact sequence where we take the localization. So that's inverting all primes that are not P. And if you localize and then tensor with Z mod P, it's the same as if you didn't localize and tensor with Z mod P. Okay, so we've got this short exact sequence. And this was another way to get our Bachstein spectral sequence, was from any nice short exact sequence like this. So our Bachstein spectral sequence looks like E1ST I guess here we're just going to have the cohomology mod P, right? And this will cook up for us the cohomology of the localization. And in this case, this converges strongly because each of the E1 ST are finite. I guess technically it converges, this is for all S and T. I guess technically it converges to the completion, but the completion and the localization are very closely related. In particular, the P torsion in both of them is exactly the same. So Z mod P to the N is P complete. And the only difference is going to be the free summands, but we're ultimately going to be trying to detect those as things that live forever in the Bach-Stein spectral sequence, and we would ultimately want to get back to that integrally anyway. So do I care if they look like Z localized at P or Z completed at P? No, it doesn't really matter in this particular case. Okay, so that's basically all I'm going to say about convergence. Again, there's a lot of good stuff in McCleary and Boardman, so look there, especially if you find yourself dealing with a spectral sequence that's a little bit more complicated or convergence is more complicated. But the overarching thing that I want you to remember is that we really can only see the completion on the E infinity page. The spectral sequence can't tell the difference between the completion and not completion. And in the nicest bounded cases, then yes, we get really strong convergence. And in a lot of other cases, really, we get that too. And that's where we just have to solve extension problems. We don't have to deal with lim1 terms. We don't have to deal with complicated stuff. Okay, I will stop there.